Hi everybody, welcome to Friday lecture. I'm going to be talking today about the Rankine cycle. This will be our second and final lecture about Rankine cycle. As I said, I'm going to be trying to do 2 lectures per chapter. Wow, that's really tight, but that's what we're going to do. I'd like to get through at least a couple of my favorite gas cycles and get through Rankine cycle today, which I can do because I'm skipping a bunch of chapter 8. I'm only going to be talking about the reheat cycle, which you can see here as an example. Superheat, reheat, and then some irreversibilities, or things that might cause friction or losses in a Rankine cycle. So those are the things we're going to be talking about today. So not going to be covering a lot of the other stuff that's in the text, but at least we'll cover the main points of Rankine cycle. So let's see. First of all, let's look at here. This is from yesterday's lecture. So what the Rankine cycle best approximates which practical power producing system? Well, half of you, more than half, the majority of you picked gas turbine power plant. If you were to Google gas turbine power plant, if I can do that. Let's see. Let's just in a new tab. Let's see. What does not let me in a new tab? Oh, here. Let me just create a new tab, okay? And let's Google search gas turbine power plant. And cycle. We can see the gas turbine basic operation of the gas turbine power plant is the Brayton cycle, which we haven't covered yet. That's chapter 9. Okay, so the gas turbine is not what we're covering. There is turbine in a Rankine cycle, but it's not a gas turbine, right? This isn't an ideal gas cycle. This is a steam cycle, a cycle that's used as a vapor power cycle, okay? So my point is, gas turbine power plant is not correct. Internal combustion engine? Well, 2 of you thought that, but that's wrong. Nuclear power plant? Definitely. We're definitely using the Rankine cycle in the nuclear power plant, okay? And industrial refrigeration cycle, no, not at all. It's very actually similar to the Rankine cycle. It's just kind of backwards. It's a vapor refrigeration cycle, but okay. So we got some work to do. So the Rankine cycle, as I said in my previous slides, idealizes the steam power plant. So steam power plant. Oh, I went through a lot of slides. So a steam power plant looks like the following, right? So here's vapor power plant. This is, where's the nuclear one? Here's the solar, here's the nuclear one, right? So remember I said that I put a box around I made a dash box and I put it around the cycle? That's what's going on here. So we've got a cycle that's very similar to a nuclear power plant or a coal power plant, which is what I discussed, not a gas turbine power plant. All right, gas turbines are new, and people are doing a lot of new gas turbine stuff right now, but that is what we're going to be learning in the following chapter. Okay, so thank you for participating. Let's see, where am I going now? Okay, so we talked about boil pressure, varying boil pressure. We did not discuss this. Let's see, where did we leave off? Oh, here we go. Okay, so we're going to talk about some things we can do to improve the performance. So I'm going to just tell you these things, and you may have to figure them out yourself in some examples. I'm going to do an example of a reheat cycle today. So I'm not going to talk too much about this, but one thing we can do is to look at two cycles having the same boiler pressure by different condenser pressures. So the fixed boiler pressure is the one here, the top one, and the condenser pressure is this one right here, the low one, right? And one is at atmospheric pressure and one is below atmospheric pressure. Remember last time in my lecture I said that sometimes they draw the condenser pressure down below atmospheric pressure, which in this case they're doing. So making 2 double prime here and 3 double prime and 4 double prime, etc. Okay, back down to the ambient temperatures down here. So they can draw down to is what the temperature is below the ambient, essentially, right? Okay, so since the temperature of the heat rejection is lower than the temperature 1, 2, 3, 4, the cycle condensing below the atmospheric pressure has greater thermal efficiency, just because the area under the curve is larger. Go figure. The area under the curve is larger because it has greater heat rejection. So the reducing the condenser pressure tends to increase the thermal efficiency. So reducing condenser pressure increases the thermal efficiency. Interesting. So by the same token, increasing the boiler pressure and keeping the condenser pressure the same also increases thermal efficiency. However, we may have a problem with that. But anyways, let's finish that. So power plants condensers normally operate with steam condensing at a pressure well below atmospheric. For heat rejection to the surrounding, the lowest feasible condenser pressure is the saturation pressure corresponding to the ambient temperature. So if it's at 20 degrees C, whatever PSAT is at 20 is where you find it. And that's down pretty low. I mean, it's like less than a kPa. It's very low. The primary reason for including condensers in vapor power plants is to increase the thermal efficiency when the condenser operates at pressure less than atmospheric. Another is the condenser allows the working fluid to cool in a closed loop, so demineralized water that's less corrosive than tap water can be used. Okay, so yeah, I definitely want to make sure you don't just take water from the river and put it into your power plant, because that could cause all sorts of corrosion plant problems. So we use a heat exchanger instead. Okay, as steam condenses, energy is discharged by heat transfer to the cooling water separately through the condenser. Although the cooling water carries away considerable energy, its utility is extremely limited, because cooling water temperature is increased by only a few degrees above the ambient. So such warm cooling water has little or thermodynamic value. We say that has low availability. Like it means it has heat, but not very good quality heat. All right, so we skipped chapter 7, where we were to learn about the quality of heat. But that's okay. You can learn about that in advanced thermodynamics class later in your career if you like. That said, even if it has a lot of heat, doesn't mean that it's good, useful heat. All right, so the figure shows two cycles having the same condenser pressure but different boiler pressure. So here we go. Here's the converse, right? So if you increase the boiler pressure and keep the fixed condenser pressure, you're also going to have greater area under the curve. Now, increasing the boiler pressure tends to increase thermal efficiency. Notice that your area gets a little bit shrunken because the shape of the TS diagram, the shape of the vapor dome. So you get shrunken a little bit because you can't suck down to the straight line that takes you to 2' is a little bit to the left. Your area is a little bit reduced, but still overall it tends to increase thermal efficiency. We're going to talk about the main thing we do generally is to actually take this one and go up to superheat. So we take it to a higher temperature and use a superheater, which we're going to do an example of today. However, increase in boiler pressure also results in the reduction of steam quality for the expansion, as I just said. So steam quality at 2 is not good. So if the quality of the expanding steams becomes too low, the impact of liquid droplets in the steam can erode the turbine blades. That's not good. So another reason why we typically send the steam into the superheater is because it's all gas. You generally want to send anything that has liquid droplets in it into something that has rotating blades. Liquid droplets, when they're spinning around really, really fast, can become little projectiles that eat away at turbine blades. So generally don't want to keep it inside the vapor dome. You want to have outside the vapor dome. So Rankine modifications known as superheat and reheat permit advantages for operating pressures in the boiler and condenser while avoiding low quality steam. So avoiding this situation here, both of these situations, in fact, where you have low quality steam. This is a good point, actually, to introduce the difference between the Carnot cycle and the Rankine cycle. A student asked me a question and said, well, I don't understand the difference between a Carnot cycle and a Rankine cycle. I don't see any real difference. Well, okay, typically, if you have a Carnot cycle, it's a box in the TS diagram. It has 3 to 4 would be a constant entropy process. 4 to 1 would be a constant temperature process. 1 to 2 would be a constant entropy process, and then across the bottom, it would be a box. So Carnot, just remember, Carnot cycle is like a box in the TS diagram, okay? It's not rectangular, but it's a box, okay? So what I'm saying is that there's one key difference in the vapor Rankine cycle, and that is that this boiling process here is not isothermal. Not isothermal. It's isobaric, meaning it's at constant pressure, not at constant temperature. You see, it's only constant temperature across the dome. you could make a Rankine cycle like a Carnot cycle and make 3 inside the box. So you could make, if I just put Carnot cycle inside, and let me just make a box inside there, you could put Carnot cycle inside here like this, right? You could say, well, this is my Carnot cycle inside here. So no fill, and then I'll just make it red or something, red for a Carnot cycle. Now, you can say, this is great. I got a Carnot cycle. Oh, you're not going to see that. So let's make it like this color. All right, so you got that's still not good. So anyways, here's your Carnot cycle inside. So we could just call this a Carnot cycle. Oh, it's going to be white. Okay, so here's Carnot. We could just say that the Carnot cycle is this square. Here, let's go. Where's my text? It's not going to show me my text, is it? Oh, here it is. Okay, so Carnot's here, and you can say it's a box, and you move it in here, and then you can make the Rankine cycle like a Carnot cycle. However, the problem with this is that you don't really want to be pumping two-phase stuff, because two-phase stuff is a bubbly mess, and as I said, you'll ruin pumps and compressors, and you don't want to expand it either. It'll erode the performance of the practical performance. So typically what you want to do is you want to operate like this. Your Carnot cycle to operate like this guy, right? Where these things are outside the vapor dome. The problem is that there's no practical way. You see the blank between 4' and we'll call this 4 double prime or whatever here, and this top piece, and then this whole area. So there's going to be some area where you're not going to have the heat. So you don't actually have that heat. So it's less efficient. So what I'm saying is that the Carnot cycle is more efficient than a Rankine cycle at over the same pressure ratio. And you could say that probably, you can say that probably you could take like an average temperature, like here, you could say that's the average temperature, and this would be your Carnot cycle. But what's the point of that, really? You can analyze a Rankine cycle pretty easily. So the Rankine and the Carnot are very similar, except for that one piece in the boiler is isobaric and not isothermal. That hopefully answers people's questions. Probably confused the heck out of some people too. But I'm just going to Carnot as a box. I'll just leave it on my slides, and I'll update those slides later. Okay, now, what happened here? I got some formatting. Okay, now let's move on so I can get some example problems today. So Rankine modifications known as superheat and reheat permit advantages. So this is the thing that we're going to talk about next. Another modification is the supercritical cycle. We're not going to talk about supercritical cycle. So actually, I'm not going to. I'm just going to get rid of this. We're not talking about supercritical. Forget it. You can talk about supercritical. You can read about it later. We're not doing it because we don't have time. Okay. The main thing we are going to talk about though is the reheat and the superheat cycle. So the superheat cycle is this one right here. So you can see the one we've been talking about is this 1, 2, 3, 4, 1 cycle. The superheat cycle takes us out of the vapor dome for the expansion in the turbine, so we don't have droplets in the turbine, and moves us up into a superheated condition, 1', and then drops us back down to 2' for the process. So the TDS here, also greater heat addition, right? You end up getting higher average temperature of heat addition, so you actually increase the average temperature. So if you think about it like a Carnot cycle, and the average temperature at the peak TH increases, you get higher efficiency. So that does definitely increase your efficiency. So the cycle average efficiency for a superheat cycle is much better. A combined boiler superheater is called a steam generator. So yeah, I don't know. I guess I always thought the boiler contained a superheater, but I guess superheater is a separate thing, so it just generates steam, right? Because the boiler just implies boiling. Okay. Oops. So another thing we can do, in addition to superheating, is we can use what's called a reheat cycle. Okay, so I'm going to leave this here. I'm going to put myself over here or something. Okay, so the reheat cycle is another Rankine cycle modification that takes advantage of increased thermal efficiency resulting from high average temperature of heat addition. So why not just like have two turbines. So in this case, two turbines attached to a common shaft, and then you go back in. So you come out of the boiler, you go into the so 6 to 1 is your first thing. So 6 goes to the boiler. Great. You boil and superheat and steam generator. You go through, make some superheated stuff. You go into this first stage of the turbine, and then you come out. But then you don't go right to the condenser. You go from there into a secondary stage of heating called a reheater. And the reheater is just another set of tubes inside the boiler box, way up high, where it reheats the steam coming out of the high, we call the high pressure turbine, and then sends it into a low pressure turbine. And then you've got, which is usually a bigger machine, makes more power. And then send it, then from there, expand it down below atmospheric pressure into the condenser and then into the pump again. So this actually really helps because you can actually keep this temperature high. So as opposed to just having this thing drop, you can actually extend the diagram to the right and keep reheating. In fact, most commercial steam power plants will have at least 3 stages of reheat. So they'll have 3 turbines. So they'll have a high, medium, and low pressure turbines. They're all built into one unit. It's not like separate things. They're usually on the same shaft, and they've got like different sections. So the high pressure section, the low pressure section, or the medium, and then the low pressure section. So typically we'll have 3 sections of turbines. So yeah, and different boiler reheats and steam recycles and all sorts of stuff. It gets complex. But this is actually a really good one. This is why I'm presenting it to you, because this is actually a really good way to increase thermal efficiency of a Rankine power plant. And in a really good way, and pretty easy to analyze too, as we will find out. Okay, so it departs from the simple vapor power cycle because it has the high pressure turbine, as I said, you reheat 2 to 3, and then 3 to 4 we go through a low pressure turbine stage, and then 4 to 5 we go through the condenser just like normal. So it's just one addition of one extra heat exchanger and one extra turbine. No problem, right? Okay, so when computing the thermal efficiency of reheat, you necessarily account for the total work developed in the 2 turbine stages, 1 to 2 and 3 to 4. So you got to have the total work and the total heat added during the vaporization. So this is a process of 6 to 1 and 2 to 3. So 6 to 1 and 2 to 3. You got to include both of those. So then your efficiency equation becomes a little bit more complex. But as you'll see in the analysis, it actually is not that complex. So let's do the analysis. So I'm, 18 minutes in here. So let's just do the analysis right now, and we can hopefully do a thorough job of this and do a good job of the example. And then I'm going to talk to you about irreversibilities, and then we're done. And irreversibilities won't take us very long. Okay, so let's get to my example. All right, so in this example, we're going to deal with a reheat cycle. As you can see, I've cheated. You can see I've cheated. I've actually taken my I've taken the diagram here and I've copied it from a solution manual. So I don't have to redraw it because it's so pretty. I didn't want to make my own diagram, but I expect that you guys will make your own diagrams of these things. I'm saving myself some time here so I can go through the analysis. The other thing that I'm going to do to save myself time is I am not going to go paging through the steam tables to find all the states. I trust that you guys know how to do that by now, okay? You know how to look through the steam tables and find quality and look for superheated steam and saturated steam, and you just go crazy. You can do it, okay? So I'm not going to go looking through the steam tables today. All I'm going to do is I'm going to do the analysis of this reheat Rankine cycle. So it's an ideal Rankine cycle with reheat, but it also includes superheat. So this case we have reheat and superheat, but it's still ideal. When it's ideal, that means that we assume isentropic expansion and compression and reversible processes throughout. Okay, so that makes things easier to do the analysis. Steve expands to the first stage at 1 megapascal and reheated. So we have we see the reheat temperature and the initial steam boiling superheat temperature are the same, but the pressure is reduced, of course, because it's low pressure. 10 megapascals to 1 megapascal. And then we have to calculate the heat addition in entering the first stage of the turbine. the thermal efficiency and the heat transfer from the working fluid passing through the condenser to the cooling water. All right, so that's fine. We can do that. All right, so let's go here. Heat addition. So water is a working fluid of an ideal Rankine cycle with reheat. Heat addition. So we have, we'll just say known. We have an ideal Rankine cycle with reheat and superheat. We have to find heat addition to the first stage of the turbine, so that we'll call this QT1. We're going to call it the thermal efficiency of the cycle, and we're going to call the heat transfer from the working fluid passing to the condenser and the cooling water. So we'll call this QC. Okay, so the condenser. So the QC, they're calling it Q out here. I'm going to label this diagram differently here. Assumptions. Okay, so we're going to assume that it's an ideal cycle. One. Ideal cycle, it's steady state. It's a steady cycle. So it's an ideal cycle. So we have all that stuff that goes with the ideal cycle. So I don't have to, oops, I'm just going to say ideal Rankine cycle. So I have to write all the assumptions, you know, isentropic turbine, isentropic pump, reversible this, and blah, blah, blah. Let's just leave it at that. We know what an ideal Rankine cycle is, at least I know what it is, and you guys should know what it is, so that's fine. All right, so here's my diagram here. All right, so the diagram looks like this. Let's just move it over here. I am going to label some key things here, maybe in a different color. I'll label it in sort of this bluish color. So this is what we need to find here. So this is Q C that we just had. We also want to find the Q. What does it say? The heat addition. Entering the heat addition in kilojoules per kilogram entering the first stage. So we want to find this one, the heat addition. So Q in 1. So it's not T1. I'll get rid of this. Let's call it something else. Let's call it Q in 1. In 1, okay? And then we've got Q in 1, and then we got QC. We are going to assume here that we have all these different control volumes. You notice that they all have little dots around them, because we take the control volume of all these different items here. So you notice that we're not given mass flow, right? So everything that we have is divided by mass flow. So it's the power divided by mass flow. So these are all the different control volumes. And these are the states, right? So we have state 1, state 2, state 3, state, see, where's 4 here, 5, and 6. And the pressures are given on the table, in the diagram, okay? Always good to label the temperature and pressure that you have. The other thing we have to do, of course, is we have to make our TS diagram. Always have to make our TS diagram. So let's just make it here. Okay, so our TS diagram is here. We're operating, in this case, on 3 different pressure levels, not just 2. So we have the very low pressure, which is in the condenser side. And this is at 8.08 bar. We have another pressure that operates at 1 megapascal, so that's here. And we have another one that operates here at, so this one, so these are the 3 pressures. So this is at 10 bar, and this is at 100 bar. I don't like, let's see, these aren't right. It actually looks more like this. Right? Kind of looks like that, right? Okay, you can fix my diagram. All right, so now let's label, the next thing we got to do is we got to label our states on the diagram, okay? Labeling our states in the diagram is an important thing to do. Okay, so then we're going to start with point 1, which is at the high temperature, high pressure point. So point 1 is like here. So this is at, we're going to call this, what did we say, 320? And then we zap over here, and this is also the thing for the next one as well. So we're dropping this one down to here. So 2, that's supposed to be straight, okay? Yeah, it's sort of straight down. And then 2 to 3 goes from here to here. And then 3 drops down here into 4 is here. And then I'm going to just get rid of that, and I'll make a color version. And then from 4, we have to go to 1. So for the 1, we always assume for the ideal, 4 to 5. 5 is here. 5 is the point at which you condensed all the way to get to saturated water, and then we got to pump. So we're going to pump up to the high pressure, right? We're going to pump up to the high pressure 6. We're not pumping up to the lower pressure because that doesn't make any sense. We're pumping the high pressure. So if I just make a where's 1? So there's 1. So if I just put this in color, let me just put this sort of like an orangey color. We can just follow it. So we have 1, 2, and then 3, 4, 5, 6, and then 1, like that. Okay. This is we're gonna call this one 3 here. Okay. Do I have all the states? Okay. I've labeled all the states. I have all the temperatures and pressures. It would be nice to put some arrows on here, so we know what's going on and which direction everything's going. But okay. So we did that. All right, so that's pretty much what we have to do in terms of that. Now, we have to analyze all the states, okay? So what I typically do is I'll just put together all the states, and I'll start with state 1, because we're given state 1 in the problem. So analysis, we'll start with state 1. Okay, starting with state 1, we've got the pressure of 1, so P1 equals 100 bar. And then T1 equals 320 degrees C. You look in the superheat table, right? Table A4. Table A4, and then you can get the H1, which is equal to, I'm just copying this down, 2781.3 kilojoules per kilogram. And S1 is equal to 5.7103 kilojoules per kilogram. Right? Then we'll go to state 2. So that's pretty easy. That's superheat. Right? So that's superheated steam. So we go to state 2. We have P2 equals 10 bar. And T2, let's see. T2, we don't know T2 yet. Well, yeah, we do, because we're dropping into the saturated, right? So T2 is saturated. T2 equals Tsat at 10 bar. Was it T2 is at 10 bar, right? At 10 bar. Which is, if I look at my thing here, do they even tell us what that is? Let's see, in my solutions. Oh, they're not going to tell me what that is? No, they're not even telling me what that is. I guess it's not important for the analysis. We only need to know the enthalpy. Really just need to know the enthalpy. But so we negative the enthalpy, we got to find the quality. So to do that is you assume that S2 is equal to S1, and this one. So if we look at table A3, and we look at X2 at pressure of 10 bar, S2 minus SF2 over SG2 minus SF2, and this is the quality. So we can get the quality by just putting these values in. 5.7103 minus 2.1387. This is looking up that. Those are looked up in the tables. And the SFG is 6.586 minus 2.1387. And then we can get the quality. So the quality then X2, quality X2 is then 0.803. Looking back here, well, it doesn't look like 80. It looks like about 90 according to my diagram. But okay, did fine. So it's about 80% quality. Then H2 then, so H2 is equal to HF2 plus X2 HFG at 10 bar. So then bar. So then again, looking at the table, we can calculate it. So 762.81 plus 0.803 times HFG, which is 2015.3. Okay, and this ends up being H2 is equal to 2381.18 kilojoules per kilogram. Okay, and then of course we got to move to state 2. So this is what you do. You just go through this. You go through this exercise, and you go through the ideal Rankine cycle by going through from state to state. So P3 is also equal to 10 bar, and T3 is equal to 320 because it's reheated to 320 degrees C. So now we're back in the superheat table. So we look up table, we look up table A4 again. And looking up in A4, we have H3 is equal to 3093.9 and S3 is equal to 7.1962 kilojoules per kilogram K. Okay, so then we do the same exercise for state 4. So state 4, we know that state S4 is equal to S3 because we've got an isentropic turbine, right? I'll just write that down. Isentropic turbine. Okay, so we have an isentropic turbine. And then so we drop that through there, and so we can get, so P4 is equal to 0.08 bar, which is really low pressure. And we know that if we just solve X4 equals S4 minus SF4 over SG4 minus SF4. And I'm not going to plug those in because you can figure those out. And you can figure those out for yourself. And so this ends up being, becomes 0.086, I mean 0.86, so 86% for 8. Okay, so then H4 is equal to HF4 plus X4 plus HFG4. And then this ends up being, if we look this one up, we can get 2252.08 kilojoules per kilogram. All right, so now we're almost there because we have state 5 is saturated, right? So back up here, state 5 is here at the saturated point. So we go back down, state 5 is P5 equals 0.08 bar. And we have saturated liquid. So then we definitely know where we're at. So H5 equals 173.88 kilojoules per kilogram. And S5 is equal to, what is S5? We need to know S5 because we have isentropic pump. So S5 then is equal to, oh no, we do VDP. We can do VDP for isentropic. So V5 equals 1.0084 times 10 to the negative third meter cube per kilogram. Okay, so it's essentially 1,000 kilograms per meter cube like water. And then state 6. So then go to state 6 and we got H6 is essentially equal to H5 plus VDP. P6 plus P5, right? And then in this case, so H6 is equal to 173.88, which we found from up there, which is H5, plus 1.0084 times 10 to the negative 3, times the difference in pressure, which is 100 minus 0.08. And I believe we need a 100 in here because we're at bar to kilopascal, so we got to go 100. There's 100 bar per kilo. Oops. Where are we? 100 kPa per bar. Oh, this is my second example that I want to do, so I'll move that down. Okay. So then here we have H6 then is equal to 183.96, and that's all we need. So to summarize this, I'm going to just put this handy table in here that I found from the solutions, right? So then here's a table. I just pop this in there. So then you got all the different values that we just found. Okay, so this is the summary of all the states. All right, so let me just say, so this is example continued, and this is a summary, okay, of all the states. All right, so then you can refer to that. And then what we got to do is we got to go through and find what we need to find. Now, I'm going to leave this as an exercise. But what we need to do is we need to find what Qin is. So Qin, so for A. So now we can solve the problem. Now we have all the states, we can solve the problem. So Qin is equal to, well, it's Q dot in over, well, we're going to, what are we calling it? We're Q dot, I think we're calling it Q dot, what did we, I got to make sure what we called it here. Q dot in 1. Well, I think they're calculating Q dot total here, so I'm not sure. For the control volume enclosing the steam generator. So if you think about the steam generator, it goes 1 to 6. So I guess they're calling this whole thing, I misread the question. So this thing, whole thing right here is Q in, right? All right, so let's just do that. So we're going to find Q in. So Q in, which is Q dot M over N, M total is the mass flow rate, right? So this is in kilojoules per kilogram, right? Because it's watts divided by kilograms per second, which gives you kilojoules per kilogram. So this is equal to H1 minus H6 plus H3 minus H2. Right. So if you look here, just think. So there's H1 minus H6 and H3 minus H2. Okay. It's 1 minus 6, right? Because that's what our sign convention is, and that'll be heat in. Okay. So then if we just put our values in here so that we can get this number. So 2781.3 minus 183.96. Plus H3 minus H2 is 3093.9 minus 2381.2. And this ends up giving us 3310.1 kilojoules per kilogram. Okay, so then, so that's part A. Part B is finding the thermal efficiency. So this is equal to little w over Q. And little w is, well, we can say little w is Q out minus Q in. And Q out is the Q in the condenser over Q in. So work of the cycle. So this is total work of the cycle, including the work done to the pump, right? So, but you can just use the first law for a cycle to get this easier. So H1 minus H2 plus H3 minus H4 minus H6 minus H5, right? And let's see, can we get rid of anything in here? No, I think we can't. So if we do all that and we divide this thing by just by Q in, we already have it by 3310.1. And if you add all those together and get that done, we've got essentially a thermal efficiency here value of something like 37.2%. All right, and then C, this was to find the Q for the condenser. So Q out is just H5 minus, H4 minus H5. So this is how much heat was lost by the condenser. And this is 2252.1 minus 173.88. So this is how much heat we lost to the river. this one is 2078.2 kilojoules per kilogram lost to the condenser when we condense these things out. So yeah, 37. Let's see. If we look at it here, we could have also said that this is also equal to Q minus W equals, so Q in minus W of the cycle. equals Q out, and then you get a similar answer. Okay, so that's how you do it. So pretty simple. Once you have all the enthalpies, I mean, straightforward. You need the entropies though, so because you know you need to use them to find what the quality is inside the cycle. Okay, please look through this example and figure it out. If you're not understanding what I'm doing, you'll have a way to practice over the weekend, so you can practice it. Okay, so then in my remaining time, what I want to do is I have about 10 minutes. So what I'm going to do is just going to go through the one last thing we want to talk about, and this is pretty obvious. The ideal Rankine cycle has no irreversibilities, all reversible processes. There are irreversibilities, big time, in any system, especially a big power plant like this. So a fossil fuel power plant, by far the most important irreversibility is the combustion and the subsequent heat transfer from hot to cold. But those are outside our system boundary, so we don't care about them so much. We mostly care about the irreversibilities inside our system, okay? So if you think about what's inside our system, what we're talking about are mainly irreversibilities associated with the turbine, and that would be friction, okay? So the most significant internal irreversibility is through the turbine, where you have some friction, and luckily, last week we went through the efficiency, the first law of efficiency of the turbine and compressor subsystems. So we should be able to easily analyze how we do this, because remember this, the work of the turbine, the efficiency of the turbine is equal to H1 minus H2 divided by H1 minus H2S, where H2S is the isentropic enthalpy, so where S1 equals S2S. Okay, so we can easily figure this out using a turbine, and we can also do the same thing for the pump, and we say that we just have the reciprocal of that efficiency for H4S minus H3 over H4 minus H3. So this is a pretty simple thing to do. We introduced these in chapter 6 when we went through that after our exam, and so you should definitely be able to calculate these isentropic efficiencies pretty easily because you've done that recently. So what if, oops, I just lost my iPad here. So if okay, oops. All right, I think I got it. Okay, so now what we do, what if, oh yeah, there's also one more. For simplicity, frictional effects resulting from pressure reductions are ignored in chapter 8. Flow these components assumed to be at constant pressure. This doesn't happen, as I said. There's pressure drop through those things for sure, and that's another irreversibility is pressure drop. But we're not going to consider those things in this analysis. So we're not going to consider these things in this class. So don't have to worry about pressure drop. It makes things difficult, more difficult to do, but not that much more. So what we're going to do is we're going to do one more thing before I quit, and that is we're going to do this cycle, same cycle, the previous example problem, except we're going to reconsider assuming that the pump and turbine stage each has an isentropic efficiency of 80%. So let me move this thing to another page so then I don't have to start again. So I'm going to do, I'm just going to do known. So here known is I'm going to assume that we have a known, this is not now a semi-ideal. We're going to call it, I'm going to call it ideal Rankine cycle with irreversible turbines and pump. We're going to find the same thing. I'm just going to say we're going to find the same thing. We're going to find Q in, we're going to find thermal efficiency, and we're going to find, what else we're going to find? We're going to find Q out. Right, so those are the things we're going to find, just like before, and we're going to assume, here we're going to assume that we have an ideal Rankine cycle with irreversible turbines and pump, where those are T equals no pump equals 0.8, right? We're going to assume steady state. Now, one thing we're going to do is we're going to make a new TS diagram. So we don't need to make a new system diagram because it looks the same. But if we make a new TS diagram, let's see if I can make it the same. We have the three pressures, the same pressures we had before. So just because there's our ice, oh man, I always do this. Okay, and then, right, let's see, like that. Ah, that's not right. Don't get picky here at the end of class. Here we go. All right, so anyways, we got this. We got 10, we got 100, 10, and 0.08, right? In terms of bar. All right, and then you're going to have one is here, 320. So we're assuming here that these temperatures are the same. 320 is the same, okay? And the pressure is the same, except that before, oh boy, this didn't work out very well at all. I'm going to make a new diagram here. Hold on. Like this, all right? And then I'm going to put this guy here, and then so I can drop this guy inside the dome, which it needs to do. Still not doing a very good job, am I? I'm really messing up here. So, okay, get rid of that. I need this guy to drop into the dome straight. So this is 1, 2, and then 2s is going to be like this. Right, so 2s is going to actually drop you into, is going to be a little bit different. No, actually, I'm sorry, 2s is going to be the other way. So this is 2s is straight down, and then 2 actual is going to be like this. Okay? So essentially what you've got now is you've got actual 2 is moved to the left, and then you go up to the same 0.3, and then you have 3s, which is here, and then 3 actual is sort of drops you, 3 is here and 3s is here, and then you're going to go over here to 4. Like this is 3, this is 4, 4, 4, and then this is 5, and then 5 is going to have 5, 5s, and then 5 actual is going to be, a 6. Say 6s is straight up, and then 6 is just a little bit to the right. So what did I do? Get rid of my vapor dome again. Okay, and then 6 is here, and then 6 is just a little to the right. So 6s is straight up. So if I just zoom up on this, if we have 6 is straight up, and 6s is sort of like this. Right, so this is 6, and this is 6s, and this is 6, just like that. And this is 5, okay? So zoomed up there. Just like here, this guy drops into the dome even more, okay? So if we just think about what we need to do, we already checked these states. 3, 4, and 5 are, so states 1, 3, 2s, and 4s, as well as 5 and 6s are known from previous example. So we don't have to do that. But what we do have to do, is we have to figure out what the remainder of everything is. Okay, so we need to figure out what we need to find is 2, 4, and 6 states. Okay, we need states 2, 4, and 6. All right, so in order to do that, I'm out of time. So what I'm going to do is I'm going to just do the first one, and then I'll post the solution for you. Okay, so then you have the solution, you can look at it. But let me just do the first one. So finding state 2. So if I want to find state 2, we know that P1 equals 100 bar, and T1 equals 320 degrees C. We know that H1 equals 2781.3, and S1 equals 5.7103. Okay, we need to know state 1, state 2. So states 1, 3. Oh, so you need state 2, 2s, right? So we know that H H2S is equal to H2 from the previous problem, which is 2381.2 from previous example, kilojoules per kilogram, right? So then if we know that, then we know that let's see, do I have the right H2S? H2S equals 2381. Right, so I know that H2 is equal to H1 minus the efficiency of the turbine minus H1 minus H2S, right? Because efficiency of the turbine is equal to H1 minus H2 over H1 minus H2S. Hopefully that makes sense, okay? So then what we got to do is we just got to solve this thing because we have everything we need. We have H1 and H2S, and we can find real H2. So H1, so H2, if we just put in the numbers we have, is 2461.2 kilojoules per kilogram, right? And then we do the same thing for state, so state 3, we know, because state 3 is P3 equals 10 bar, and T3 is equal to 320 degrees C, right? And then we do the same thing for that. And we find H3 is from before, and S3 is from before. And then what we do is we know that for state 4, we know that H4S is equal to what we had before. So H3 was 3093.9, S3 is 7.196, which we don't really need. H4S, what is H4S? 2251.1 kilojoules per kilogram. And then we know that H4 is equal to H3 minus efficiency of the turbine times H3 minus H4S. Hopefully you got that. Okay, so this is what we got. So then H4 then is equal to 2420.5 kilojoules per kilogram. Okay, and then state 5 then. How am I doing time-wise? Oh, I'm over. So state 5, then P5 equals 0.08 bar. And H5 is equal to 173.88. H6S, so state 6. So H6S essentially is equal to 183.96 from the previous example, right? Kilojoules per kilogram. And then we have, the thing is that the efficiency of the pump is the inverse, right? H6S minus H5 over H6 minus H5 equals, so here yields H6 is equal to 186.5 kilojoules per kilogram. Okay, and so then all we gotta do is calculate these different things, right? So if we do it, so calculate new Q in and work cycle, and we can do that the same way we did before. Okay, so I'm going to quit now, but then essentially do it the same way before. Your efficiency ends up being lower, so efficiency, just to let you know, is we'll just call the efficiency of the irreversible cycle is equal to 30.8%. So it reduced by quite a bit with the 80% turbine. So it actually does get quite affected compared to the what did we have, 38% up here. Yeah, we had 37.2% here. And these are the final answers there. Okay, so we reduced it by quite a bit because of the irreversibilities. Okay, so that's it for Rankine cycle. I'll give you an opportunity to do a little more practice over the weekend. I'll give you a 20-pointer over the weekend that you can work on, and you can see, you try your hand at calculating all these states. It's not that hard. I recommend maybe making a table, you know, like this one here, even in Excel or something, just typing them in. It keeps your thoughts straight and keeps your numbers straight. So with that, great. Have a great weekend, and I'll talk to you again on Monday.